Okay, so today we're doing a deep dive on something I bet you think you already know a lot about hydrogen. We've got a ton of articles and excerpts, even some pretty intense research papers on it.
Yeah.
But this isn't just going to be about what hydrogen is, like the basics.
Right.
It's about the really surprising role it's played in how we figured out what atoms even are in the first place.
It's true.
Trust me, the story of hydrogen is way more exciting than just some boring entry on the periodic table.
It really is. What I think is so cool about hydrogen is that it's kind of been this unsung hero throughout like the entire history of science.
Yeah.
It's so fundamental to how things work that it just keeps popping up at these like really crucial moments, almost like it's pushing our understanding of the universe forward.
Yeah. And it's something we all learned about in school, right?
Right.
Like simplest element,
Yeah.
one proton, one electron.
Yeah.
But who knew it was practically a celebrity in the world of atomic theory? It's like even those ancient Greek philosophers, when they were talking about atoms,
Yeah.
they were kind of onto something, weren't they?
Oh, definitely. I mean, they were on the right track, even without all the fancy tools and stuff that we have today to actually prove anything.
Right.
But then, like, fast forward to the 1800s, and that's when we meet John Dalton.
Okay.
And he really puts hydrogen on the map, scientifically speaking.
Okay, so this is where atomic theory really gets going.
Exactly.
But what does that have to do with hydrogen specifically?
So Dalton, he wasn't just saying atoms exist,
Right.
He was actually trying to, like, build a system, a way to make sense of all these different elements. And the way he did that was he used hydrogen as his baseline.
Okay.
He gave it an atomic weight of 1, and that was huge because it meant every other element's weight was now relative to hydrogen.
Oh, wow.
So it's like hydrogen became the ruler, the standard, for the entire periodic table.
So hydrogen wasn't just an element, it was the element, at least when it came to figuring out all the rest of them.
Exactly. And that set the stage for so many other discoveries to come, because once you can measure and compare elements, you can start asking those bigger questions.
Right, like what's going on inside these atoms.
Exactly.
Which brings us to J.J. Thomson and the late 1800s, right? Oh, J.J. Thomson, the plum pudding model. I have to admit, that's one bit of like atomic imagery I actually remember from school.
It's definitely a memorable one.
It is.
And while it wasn't completely accurate, Thomson did make a huge discovery, the electron.
Okay.
So suddenly atoms weren't just these solid little balls anymore. They had stuff inside them, smaller particles.
Okay, that makes sense. But how did they figure out where these electrons were inside the atom? Like, it's not like they had tiny little microscopes back then,
Right.
to zoom in and look.
That's where hydrogen comes back in, along with Ernest Rutherford and his famous gold foil experiment in the early 1900s.
Okay, the gold foil experiment. I've heard of this.
So picture this: Rutherford is firing these tiny particles called alpha particles at a thin sheet of gold.
Okay, I'm picturing it.
It's like, shooting a BB gun at a piece of paper.
Right, you'd expect the BBs to go straight through.
Exactly. And most of them did. But here's the wild part. Some of those alpha particles bounced back.
What?
Deflected at these crazy angles.
Way!
It was like those BBs were hitting something solid and bouncing off.
That must have thrown a wrench into things.
It meant that everything they thought they knew about atoms was wrong.
Wow.
And that's how Rutherford realized that the atom's positive charge and most of its mass must be concentrated in this tiny, dense center, the nucleus.
The nucleus was born. So which simple element became like the perfect example of this new model?
What do you think?
Let me guess. Hydrogen. It's so simple. One proton and one electron.
You got it. Hydrogen was like the poster child for this new nuclear atom.
It all makes sense now.
But there was still this one puzzle nagging at scientists, something called hydrogen's emission spectrum.
Okay, the spectrum. That's where you get those specific lines of color, right?
Right. Not just a rainbow, but like a barcode of light. Yeah.
Exactly.
Each element has its own unique one.
How did that lead to another breakthrough?
So that's where Niels Bohr comes in, also in the early 1900s.
Okay.
He was trying to figure out why hydrogen spectrum looked the way it did.
Okay.
And his big idea, his breakthrough, was that electrons can only exist at certain energy levels within the atom. Imagine it like a staircase.
Okay.
Electrons can only be on the steps, not floating around in between.
So electrons are picky about where they hang out.
Exactly. They have good taste in real estate.
But what does that have to do with the spectrum, those lines of color?
Those lines are like snapshots of electrons jumping between those energy levels. When an electron absorbs energy, it jumps to a higher level, like going up a step.
The staircase, got it.
And then when it releases that energy, it drops back down, emitting light at a very specific wavelength.
And that creates one of those lines in the spectrum.
Exactly.
So each line of color is like a signature telling us exactly how much energy that electron lost as it like hopped down a level.
Precisely.
That's pretty cool.
It is really cool. And Bohr's model, which got refined later on, of course,
Right.
was a huge EC step towards this wild new theory, quantum mechanics.
Quantum mechanics. Isn't that the idea that the world of atoms plays by different rules than the everyday world that we experience?
Exactly. Think of it this way. In the normal world, we can predict where a ball will land if we throw it, right?
Right.
But in the quantum world, things are fuzzy.
Fuzzy.
We can only talk about the probability of finding an electron in a certain place.
Mm-hmm.
It's like the electron is smeared out, existing in multiple states at once.
Okay, my brain is officially a little bit blown.
And we're just getting started.
We are.
Because next we're diving into the world of hydrogen's hidden talents, its isotopes. Get ready for a twist, because it turns out hydrogen isn't just one thing.
Oh.
It actually comes in different versions called isotopes.
Okay, isotopes, different versions. You're going to have to back up a sec for me.
Sure, no problem.
It's like all of a sudden I'm back in high school chemistry and failing miserably.
Don't worry, it's simpler than it sounds.
Okay.
Think of isotopes, like atoms with a secret identity. They're still hydrogen, but they have a different number of neutrons in their nucleus.
So same atomic number, different atomic mass.
Exactly.
Okay, so it's still hydrogen, just a little bit heavier.
Yeah, and that little difference makes a bigger difference than you might think.
Really?
Take deuterium, for example. It's also known as heavy hydrogen.
Okay, I think I've heard of that.
It was discovered back in 1931 by Harold Urey, actually won him a Nobel Prize.
Wow.
He figured out that there's this form of hydrogen with an extra neutron in its nucleus.
So one proton, one neutron, one electron. That's deuterium's secret identity.
Exactly.
What's so special about it? Why does that extra neutron matter?
Well, for one thing, it makes deuterium about twice as heavy as regular hydrogen.
Okay.
And it forms what we call heavy water.
Like instead of H2O.
Exactly. It's D2O.
So it's still water, just heavier.
Yep. Still water, but with a higher freezing and boiling point.
Okay. So is that it?
And this is where things get really interesting.
Here we go. Another one of those hydrogen quietly shaping history moments.
You got it. Turns out heavy water is crucial for nuclear research, especially back during World War II.
Wait, what? Water? Even heavy water? How does that even factor into nuclear research?
It's all about those neutrons.
Go.
Heavy water is incredibly good at slowing down neutrons.
Okay.
And that is essential for controlling a nuclear chain reaction, like in a reactor.
I never knew that.
Yeah. During the war, the Allies found out that Germany was trying to build a reactor using heavy water.
To do what?
To produce plutonium potentially for weapons.
Oh, wow, that's getting serious.
And the Allies knew they had to act fast.
What'd they do?
In 1943, a group of incredibly brave Norwegian resistance fighters, with some help from the British, pulled off this daring raid on a heavy water plant in Vemork, Norway.
They were after the heavy water.
Yeah, they sabotaged the plant and set back Germany's nuclear program significantly.
Wow. So this seemingly small difference, like one extra neutron in hydrogen,
Yep.
actually had massive implications for the outcome of World War II.
Absolutely. It just goes to show how something that seems like a minor scientific detail can have these huge ripple effects in the real world.
It's kind of mind-blowing when you think about it.
It really is. But deuterium's not the only hydrogen isotope with a story to tell.
Oh, there's more.
Oh, yeah. Let's move on to tritium, the radioactive sibling.
Tritium. Okay, that one rings a faint bell, but I'm drawing a blank on what makes it so special.
Think back to those glow-in-the-dark exit signs you see in buildings.
The ones that eerily glow even when the power's out.
Yep, that's often tritium at work.
Seriously.
Yeah.
Those signs are radioactive. I've been standing under those my whole life.
Don't worry, the amount of radiation is extremely low, perfectly safe for everyday use.
Okay.
Tritium is radioactive, but in a way that's actually really useful.
Okay.
As it decays, it releases these low-energy particles that can make certain materials glow, a process called radioluminescence.
So tritium, one proton, two neutrons this time.
Right.
And it's radioactive. That sounds a bit more intense than deuterium.
It is, and because of that radioactivity, tritium gets used for all sorts of things.
Like what?
Scientists use it to track environmental processes, date groundwater, even study how cells work in our bodies.
Wow, it's really that versatile.
Oh, yeah, and yes, it's also used in nuclear research, especially in fusion reactions.
Fusion reactions, isn't that like what powers the sun?
Exactly. Tritium is a key ingredient in nuclear fusion. which has the potential to be this incredibly powerful and clean energy source.
So we've got this one element, hydrogen, and its isotopes are helping us understand climate change, powering exit signs, and maybe even hold the key to clean energy in the future.
Pretty impressive resume, right?
That's a pretty impressive resume for something we thought we already knew all about.
And we're not even done yet.
We're not.
It gets even more interesting when we start messing with hydrogen's temperature and pressure.
So we gone from atoms to isotopes to like international espionage.
No, right?
All thanks to hydrogen.
It's wild.
What else is there? What haven't we covered yet?
Well, you might think we've talked about all the cool stuff, but
Yeah.
we haven't even touched on what happens when you push hydrogen to its absolute limits.
Push it to its limits. What does that even mean? Like, how far can you stretch an atom?
Not stretching exactly, but think temperature and pressure.
Okay.
Like we normally think of hydrogen as this gas, right?
Super light, floaty.
Exactly. But under extreme conditions, it can totally transform into something completely different.
Okay, I'm listening. What happens when you, like, crank up the pressure on hydrogen? Does it just squash into a tiny little ball?
Way more exciting than that. Imagine this. It's the late 1800s, and this Scottish scientist named James Dewar,
Okay.
he's obsessed with liquefying gases,
Liquefying.
turning them into liquid.
Okay.
He'd already done it with oxygen and nitrogen, but hydrogen, that was the holy grail.
I can only imagine what that lab setup must have looked like.
Oh, I bet it was something else.
Bubbling flasks, crackling electricity.
Probably some dry ice in there, too.
It's like a Frankenstein movie waiting to happen.
It was like cutting-edge science at the time.
Right. So what's so special about liquid hydrogen? Why go through all that trouble?
Well, besides being ridiculously cold,
How cold are we talking?
we're talking negative 252.87 degrees C.
That's insane.
Liquid hydrogen is incredibly energy dense.
What does that mean?
It packs a huge punch for its volume, which is why it's a key ingredient for rocket fuel.
Ah, that makes sense.
Gotta get those rockets up into space somehow.
Right. They need all the energy they can get to break free from Earth's gravity.
Exactly.
But you know what I don't get?
What's that?
Our sources were mentioning something about different types of liquid hydrogen, something about ortho and para.
That's right. Even as a liquid, hydrogen likes to keep things interesting. It can exist in these two different states, orthohydrogen and parahydrogen.
What's the difference?
It all comes down to the spins of the protons in the nucleus. And I won't bore you with all the technical details, but...
Please bore me. I'm very interested.
Okay, well, the important thing is this little spin difference actually really matters when it comes to using liquid hydrogen as rocket fuel.
How does the spin of a tiny little hydrogen molecule affect something as massive as a rocket?
Well, when orthohydrogen converts to parahydrogen,
Yeah.
it releases heat.
Okay.
Now imagine you're a rocket scientist and you've got this fuel tank full of liquid hydrogen,
Okay.
but it's slowly converting from ortho to para and releasing heat as it goes.
Oh, no.
Yeah, that heat could actually cause the fuel to boil off.
Which is bad because
Not exactly ideal when you're trying to launch a giant rocket into space.
that sounds like a recipe for disaster.
Yeah, explosions on the launch pad aren't exactly great PR for a space program.
Not at all. So how did they solve that problem?
With some really clever engineering, of course.
Of course.
Scientists figured out ways to convert most of the orthohydrogen to parahydrogen before putting it in the rocket.
And that solved it.
Yep, made for a much more stable and efficient fuel.
It's amazing how much science goes into something we take so for granted.
I know, it's pretty incredible.
But speaking of pushing limits, what about this metallic hydrogen I keep seeing in our sources? Is that even a real thing?
That's where things get really mind-blowing.
Even more mind-blowing than the rest of this.
Even more.
Okay,
Yeah.
you've got my attention.
For decades, physicists have theorized that under enough pressure, hydrogen could actually transition into a metallic state.
What kind of pressure are we talking about here?
We're talking pressures greater than what you find at the Earth's core.
Okay, so like really, really high pressure.
Exactly.
Okay, but what would make hydrogen act like a metal? Like, does it suddenly become all shiny and start conducting electricity?
You're getting it. Metallic hydrogen is predicted to be a superconductor.
Superconductor. Remind me what that is again.
It means it can conduct electricity with zero resistance.
Zero. As in no energy loss at all.
You got it.
And why is that such a big deal?
Right now, the only superconductors we have only work at super low temperatures.
Okay.
And it makes them expensive and really impractical for like widespread use.
So we can't really use them for anything.
Right. But now imagine a world where we could transmit electricity with almost no energy loss, power our cities with incredible efficiency.
Yeah.
We could even revolutionize transportation.
How?
Things like levitating trains.
Okay, now I'm getting why this whole metallic hydrogen thing is causing such a stir.
It's like the holy grail of physics, a room temperature superconductor.
But has anyone actually managed to make it? Or is it still just theoretical?
That is the million-dollar question. Back in 2017, this team of scientists, they claimed to have created metallic hydrogen.
How?
By squeezing it between two diamonds at crazy high pressure.
Diamonds? Are we talking about some next-level jewelry making here?
Not exactly. Diamonds are just the hardest material we know of, which makes them perfect for creating that extreme pressure.
So did it work? Did they actually create metallic hydrogen?
Well, the results of that experiment were met with a lot of excitement, but also a lot of skepticism.
So people didn't believe it?
It's hard to say for sure. So far, no one has been able to replicate their results definitively.
So metallic hydrogen, still a mystery then?
For now, but a mystery with the potential to change the world as we know it.
It really makes you wonder what other secrets is hydrogen hiding, right?
Right. It's incredible to think something so simple can be so complex.
I know. I have to admit, I never thought something like hydrogen could be so fascinating.
It just goes to show there's always more to discover, even in the most familiar corners of the universe.
Well said. And hey, maybe one of our listeners will be the one to finally unlock the secrets of metallic hydrogen. Who knows?
I like the way you think.
Until then, keep exploring, and we'll see you on our next deep dive.